Okay, so now let us move on to look at another application of decision making under uncertainty. So this is going to be about our choice over risky assets. Thus, this is the first example that we are going to look at, which involves portfolio optimization. And our approach is going to be the same as before. So we need a way of representing preferences over risky assets. Then we need a way to actually describe the budget constraint which is involved when choosing risky assets. And finally, we'll put them together to think about what is the optimal choice of portfolio construction. So first, let us look at preferences over risky assets. So far we have been considering the expected utility model of choice under uncertainty. This has been our focus beginning last week. But now let us think about an alternative approach that is also very popular. This approach involves describing the probability distributions by a few parameters. Now, why are we thinking about probability distributions when we are discussing choice over uncertainty? The reason is because if you think about it, what we were doing when we were looking at the insurance problem, for instance, or any other decision making under uncertainty problem that we have discussed so far, is that we were essentially having rankings over probability distributions, and we were actually thinking about which probability distribution to choose, right? Why is that the case? Because in some cases the probabilities were given and we were actually moving consumption from one state to the other. And in another example that we saw, there we were actually directly changing the probabilities of the different states, right? So essentially, all discussions of lotteries or gambles that we were having was about, okay, which probability distribution you want to choose. And expected utility model of choice actually was about a ranking of those probability distributions. So here, in contrast, we are going to be looking at not the expected utility model of choice, but basically think of probability distributions as characterized by parameters and then define a utility function as being defined over those parameters. So to illustrate how this approach works, we are going to be looking at what is known as the mean variance model, which is very popular, especially when dealing with financial economics. So how does this approach work? So when we were doing expected utility, what we were essentially saying is that the consumer's preference is going to depend on the entire probability distribution of wealth over all possible outcomes, right? Remember, this is, for example, what we said that you have the expected utility is the weighted average of the probability, where the weights were the probability of your utility over the different states of the world, right? So therefore, we needed to look at all possible states of the world. We needed to figure out what is going to be the wealth in each of these possible states of the world. And so therefore, what would be the corresponding level of utility, then weigh it with the probability. And that is how we ended up getting the expression for the expected wealth. Here, we are going to take a much more simpler approach, which is to think about we should look at certain parameters of the distribution of wealth and then think about references over those parameters. So what are some parameters that we might be interested in? This could be, for example, the mean, okay, as well as variance or standard deviation. So let us develop some notation in order to make progress. So let's consider a random variable W, which takes values W1, W2 till WS, and possible probabilities of these different states are given by pi1, pi2, pi s, right? So essentially, there are capital S states, which are numbered 1 to S, and we have their probabilities. And because this is a probability distribution, these probabilities need to sum up to 1, and each of them are non-negative. And for each of these states, we have what is the value of the random variable in that state. So we can then define the mean of the distribution as the average value of the random variable. So this is the notation that we are going to use. So we are going to denote this by mu W. So W being the random variable we are looking at. And this is nothing but the weighted average that this random variable can take, where the weights are the probability. So pay attention to the notation. This is what we are going to be using for the whole lecture. Similarly, we can define the variance as the random variable's average square deviation from the mean. So this is all standard to you. We are going to denote the variance of the random variable W by sigma square W. And this is again, the weighted average of the deviation of the random variable from the expected value of the random variable. So again, while we are taking deviation, we take square deviations. And finally, the weights are the probabilities of the different states, right? And we are often going to be dealing with the standard deviation, which is nothing but the square root of the variance. And we are going to denote the standard deviation by sigma W. Okay, so this is just for setting up the notation. I am sure that you are all familiar with the concepts. Okay, so what's the idea? So let's consider that these are two potential distributions of wealth. Okay, and here these two have the feature that they have the same variance, the one represented by the blue curve as well as the one represented by the green curve. And the only difference is here that they have different means, right? When we are looking at means and variances. So if somebody is, for example, dislikes risk and likes more mean, then that person would choose the one with the higher mean here, right? Why is this choice easy? Because if these are the only two things you care about, then the variance is the same. So that is no basis to rank over the others. And the mean of one is greater than the other. So you would basically prefer to choose the one with the higher mean. And we can also have the opposite situation where you have got, again, two distributions which have the same mean. So there's no distinction on the basis of the mean, but one of them have a variance which is higher compared to the other one. So in that case, if you dislike variances, you would want to choose the one with the smaller variance, right? So that is how you can rank these probability distributions. So more generally, rather than looking at particular cases, so we want to think about a situation where higher mean return is preferred by investors. Uh, Less variation in return is preferred. So that means less risk is preferred. And we want to think of actually modeling consumers or investors with the help of a utility function, which maps the mean and the standard deviation of the distribution into a real number, right? And this is the basis of which they rank the different distributions just by looking at the mean and the standard deviation. So you'll often see different formulations. Sometimes it is utility is a function of just the mean and the standard deviation, and sometimes it is a function of mean and variance, but these two are equivalent, right? And our implicit assumption is going to be that utility is an increasing function of mu. So this corresponds to higher mean return is preferred typically by investors, and utility is a decreasing function of sigma. This corresponds to investors disliking risk, right? So these are the two different aspects that you have. So as usual, we can plot them using indifference curves. This is how such set of indifference curves would look like. So if you compare with our discussion of indifference curves from before, you will notice two changes, right? The first change that you would notice is that these indifference curves are sloping upwards, whereas the previous set of indifference curves that we had looked at had them sloping downwards. And the second difference you would notice is that we are going to say that the more to the northwest you are going, the better off you are. In the previous case, we had that the more to the northeast you were going, you were better off. So let us understand why we have these two differences. So first, why do indifference curves slope up here where they were sloping down before? So remember, the point of the indifference curve is to connect all points which give you the same utility level or the same level of satisfaction, right? Essentially, we are thinking about bundles which give the same level of satisfaction. So basically, bundles over which our decision maker is indifferent and we are connecting them. And that is how we get the indifference curve, right? So before, when we were doing it, we on the x-axis and the y-axis, we used to have two commodities, both of which are goods, in the sense that the consumer would typically want more of each of those commodities, right? So therefore, when we were moving along a indifference curve, let's say by having one more unit of commodity one, so this was something that the consumer would have liked. And therefore, in order for the consumer to be on the same level of utility as before, you would have had to take away a certain amount of commodity 2 in order for that person to be on the same indifference curve, right? And so that's why you had the indifference curves sloping downwards. Here, on the other hand, if what we have on the x-axis is this sigma, right? That is the equivalent of our commodity 1. And what we have on the y-axis is mean return, which is the equivalent of commodity 2 if you are mapping the previous discussion of indifference curve to here, right? So suppose that you start off at a certain point, let's call this point here, and you increase a bit more of commodity 1. So here commodity 1 is equivalent of that would mean that you are increasing a bit more of the standard deviation of return, right? Now, increasing sigma means you are adding more risk in this context, and we have basically consumers disliking risk, right? So in order to be as well off as the initial point, if you are giving a higher value of sigma, that has to be compensated by giving a higher value of mu as well, right? And hence you have got the indifference curve sloping upwards. Why is the set of indifference maps such that the more to the northeast you move, the better off you are? Because in this case, you are going to have that would correspond to a movement which would lead to a lower value of sigma and a higher value of mu. Right? So that is why you want to ideally move as much to the northeast as possible, right? Sorry, northwest as possible. The idea is that if you keep on moving in this direction, the value of sigma keeps on decreasing and the value of mu actually increases. Okay, so let's look at the calculation of the slope mathematically. This will help us to verify that the slope is indeed positive, as well as give us an expression for the marginal rate of substitution, which is going to be of help to us when we are characterizing the optimal point. So as before, we have that the typical equation of an indifference curves looks like the utility function as a function of its arguments. So here the arguments are mu and sigma is equal to some constant u bar. We follow the same procedure as before. So we take differentials of both sides. So the differential of the right-hand side would be d of a constant. So that will be equal to 0. And on the left-hand side, we end up getting that derivative of u with respect to mu times d mu plus the partial derivative of u with respect to sigma times d sigma. And then if we rearrange it to get the slope of the indifference curve at a point, we end up getting d mu d sigma is equal to the negative of del u del sigma divided by del u del mu, right? So the marginal utility with respect to the standard deviation divided by the marginal utility with respect to the mean component, right? Now, del u del mu is something which is positive. As mu goes up, the utility goes up. But del u del sigma is something which is negative, right? As sigma goes up, utility goes down. And so therefore, you have this fraction is something which is negative, and you have the minus sign in front. So negative negative becomes positive. So that's why you end up with a positive slope. Okay, so this is our complete description of the preferences here, if you like. So we have on the two axes mean return and the standard deviation of return. And we have the indifference curves which slope up. And the more to the northeast northwest we go, the better off we are. And basically, this is because the higher mean return is a good, whereas higher risk is a bad thing from the consumer's perspective. And we also derived an expression for basically the slope. So this is du d sigma that is equal to negative of del u del sigma by del u del. This should be actually mu, right? So there's a typo here. Okay. So now we need a description of the budget constraint as well. So let's think about it. Let's consider the simplest possible case here when we are thinking about portfolio construction. So imagine that you have two assets, one of which is a risk-free asset in the sense that we know the rate of return for sure, and it is the same across all different states. So that's the definition of the risk-free asset. And the risky state has different rates of return depending on the state. Okay, so for the risk-free asset, the return is going to be RF regardless of the states. The risky asset is going to give a return equal to MS if state S occurs, and the probability of state S occurring is given by pi S. Okay, So therefore, the risky stock's mean rate of return is going to be denoted by RM. So that's the weighted average of the rates of return, where the weights are the probabilities. And what is the portfolio? So portfolio is basically a combination of some amount of the risky stock and some amount of the risk-free asset. So let's consider the wealth. You are dividing up into two fractions. So X is the fraction of the wealth, which is used to buy the risky stock, and 1 minus X fraction is used to buy the risk-free asset. So given X, what's the portfolio's average rate of return? So this is going to be given by a weighted average of the rates of return of the risky asset as well as the risk-free asset, where the weights now are going to be the fraction of the wealth used to purchase the two different assets, right? So this is hopefully fairly straightforward. Now, let's think about it a bit more. So if you have got X equal to 0, so this would correspond to putting all of the wealth into purchasing the risk-free asset, then the return is going to be the same as that of the risk-free asset, right? So if you put X equal to 0 here, you get that the return of the portfolio is the same as the return of the risk-free asset. The other extreme here would be if you take X equal to 1, then basically you are putting all of your wealth into purchasing only the risky asset, and therefore the average return of the portfolio is the same as the average return of the risky asset. Now, can we say something about these parameters RM and RF? Remember, here we have got this risky asset, which we are going to call stock as risky, and risk is bad. So in order for this risky asset to be purchased, it has to be the case that RM has to be strictly greater than RF, right? Why is this the case? Because suppose RM is equal to RF, then you have got basically two assets, both of which give you the same expected return, but one of them has a standard deviation of 0 and the other one has a positive standard deviation, right? In that case, definitely, because the individual is somebody who just cares about this mean and the standard deviation, then for sure we know that that person is just going to buy the risk-free asset, right? And of course, if you have got RM is strictly less than RF, then the situation is even worse, right? Then the not only is the risk higher, but the return is also lower, right? So again, this person will not buy any of the risky asset. So in order for him to purchase a positive amount of the risky asset, we require that the mean return from the risky asset has to be strictly higher than the mean return from the risk-free asset. Okay. So if that is the case, we can rearrange this and we'll get that this is X times RM minus RF plus RF, right? And if RM minus RF is actually positive, which is the case if RM is strictly greater than RF, then basically what we have is that a higher value of X, which means more of the wealth is devoted to purchasing the risky asset, will lead to the portfolio's expected rate of return to go up, right? So this is the consequence of assuming that RM is strictly greater than RF. Okay, what about the variance of the portfolio? So the portfolio's rate of return variance is given by this expression sigma x square, and we can break it up into the usual definition of variance. So here you have got the rate of return of this asset in state J, and you need to look at the deviation of this from the mean of the portfolio rate of return, which remember we have described as this Rx before. So you can put in the value of the Rx. So what happens is that if you put in this expression of Rx in the expression for the variance, this 1 minus X RF term cancels out, right? And so you end up with XMJ minus XRM whole square pi j, right? So X is a constant, so you can take it out of the summation, and this will therefore become X squared because you have here this square term. And so therefore this becomes X squared. And this expression, if you see, is the same as basically the variance of the rate of return of the risky asset, right? So therefore, we have a relationship between the variance of the rate of return of the portfolio and the variance of the rate of return of the risky asset, which is this, right? Sigma x square is equal to x square multiplied by the variance of the risky asset, right? And if we can also take square root, so then we end up getting the standard deviation version, which is that the standard deviation of the portfolio, the standard deviation of the rate of return of the portfolio is equal to x, where x is the fraction of the wealth that is devoted to basically the risky asset times sigma m, right? So if you have got x equal to 0, that means all of the wealth is in the risk-free asset, then there's not going to be any variation, right? Because all chance component is washed away. And so therefore you are going to have sigma x equal to 0. And the other extreme would have x equal to 1. Then you end up with sigma x is equal to sigma m, right? So the portfolio return has the same standard deviation as the risky asset, right? So again, what you see from here is that as x goes up, because sigma m is positive, then sigma x is also going to go up, right? So that essentially tells us that what is the trade-off here, that if you are going to increase x, so basically you're going to be having more of the risky asset or the stock in your portfolio, that is going to lead to a higher expected return, but it is also going to come up with higher risk, right? So you have to think about, okay, which of these the trade-off do you actually decide to go with? Okay, so we can also plot this in the picture that you see here. So one point that is going to lie on our budget constraint is going to involve choosing x equal to 0. So this would be the case where then you're putting all of the wealth in the risk-free asset. And so therefore you end up with Rx equal to Rf. So that's the mean return is going to be the same as the risk-free return. And the standard deviation is going to be 0, right? This is what we discussed right now. So this is one point, right? Where you have eliminated all risk and you are going to get this mean rate of return equal to the risk-free rate. Another point that you are going to have is that if you have got x equal to 1, so this would correspond to putting all of the wealth in the risky asset of the stock. In that case, as we have found that the mean rate of return becomes the same as the mean rate of return of the risky asset. And similarly, the standard deviation of the portfolio's rate of return becomes the same as the standard deviation of the risky assets rate of return. So that's going to be another point, right? Now, how do we know that this is going to lie above this point? Because remember, we have assumed that Rm is strictly greater than Rf. So therefore, this is going to lie here. And of course, sigma m is more than 0. So that's why it's going to lie to the right, right? And all the other points that we can get, and this is something that we can get by choosing different values of x, are going to be lying on the line connecting these 2 points, right? How do we know it's a straight line? Well, we can actually use this equation, right? So these were the 2 equations that we had to discuss this line. So essentially, if you eliminate x from this, that's what allows you to get this line, right? So if you eliminate x, so then you are going to have xrm minus xrf plus rf. That was the equation that you have. And if you use this second equation to eliminate x, so then x equal to sigma x by sigma m. So you end up getting that Rx is equal to Rf plus sigma x by sigma m multiplied by Rm minus Rf, right? So this is the equation of a straight line. And you can also find out what's the slope of this straight line. So this is going to be again Rm minus Rf by sigma m. And this is again something strictly positive, as we have discussed, because Rm is strictly greater than Rf. And this is also an important quantity, right? So essentially, it tells us what is the price of the risk, right? Why is it telling us the price of the risk? Because it is telling us that if you want 1 more unit of risk, then how much higher return do you get in return, right? So how much higher mean return do you get in exchange? So this is how you can interpret the slope, right? So we have now basically got the different components. What we want to do next is to actually put these 2 together, and that is what we are going to look at now.